Hey there. Okay, so now we are going to start Module 5, and the first lecture in this mini lecture in this module is recognizing and analyzing amplitude anomalies. So this is kind of getting into the DHI. So what do those bright anomalies mean, or what does it mean when the anomalies suddenly dim? So let's get into this. So DHIs, as I just mentioned, we often look for them. They became popular decades ago, maybe back in the 1970s. And they're these, not just these bright amplitudes, but these anomalous seismic responses that are often related to the presence of hydrocarbon. A lot of this is because if you go back to the introductory lectures where we talked about the velocity and the density and the acoustic impedance, when you put gas in the pore space instead of water or brine, you end up with a lower density, a lower velocity, and so you end up with a larger reflection coefficient in the shallow portions of the crust. And so that can cause a brightening of the amplitude. And so those were the first ones that geologists noticed and that they went and they drilled after. So I think it was the 1970s, they did all of this drilling for bright spots that they saw in seismic. But bright spots aren't the only DHI. We have all sorts of amplitude anomalies, from those bright spots that I keep mentioning to flat spots that can represent a fluid contact. We also have dim spots, so the opposite of a bright spot where you get a dimming, and that's a little bit deeper in the earth. Polarity reversals. We can also look for reflections due to the fluid contact, and also structural fit to contours. So kind of like we would expect the gas or the oil, since it's less dense, to pool in the upper portion of the structure. So I'm going to talk about all of those and show a lot of examples of what we look for in seismic. So just to review some of these depth trends, because they're very important for recognizing these DHIs. In the shallow portion of the earth, and here I go turning on my pointer, should really do that ahead of time. In the shallow portion of the earth, our gas sands have a much lower acoustic impedance than the shales. So if you have a gas sand sandwiched between a shale, you're going to have a large reflection coefficient. You're going to have a large bright spot. As we get deeper in the earth, the acoustic impedance becomes, the difference between them becomes much less between the shale and the gas sand. And it's actually eventually gets to a stage where the water sand has a higher acoustic impedance than the shale, which then is higher than the gas sand, so kind of right in this area. And so there we'll get a phase change when we move into the hydrocarbon portion of the reservoir. And then deeper still, the shale has the lowest acoustic impedance of all. And so we'll end up seeing a dim spot when we go from water to shale, from the water portion of the reservoir to the gas portion of the reservoir. And so I'll show you what all of those look like. And so like I mentioned, back in the 1970s, these were the thing that folks were prospecting for. And so this is just a really cool example, I think, of the quality of seismic we had in the 1970s and what they were looking for. So in this case, we've got some bright spots right in here. Here we've got what they called a dim out, but now we call a dim spot. So right at the top of this reservoir, you can see that the amplitudes are a bit dimmer than what the water lake would be. Here we've got a phase reversal, very, very tricky to see. And then down here we've got a flat spot. And so you can see that flat spot is kind of bright on top. So that would be a bright spot combined with a flat spot. And that flat spot is where you have that kind of gravitational balance of the gas or the oil on top of the water. They also started noticing back in the 1970s that there were differences between what they were seeing in the near offset data and what they were seeing in the far offset data. So starting to realize that these angle stacks played a role in hydrocarbon exploration. And so we're going to talk about that a lot more in the next lecture, which is about amplitude versus offset and those types of kind of advanced technologies. But in this case, they noticed that things got a lot brighter in the far offsets than they did in their near offsets. And so those were other indicators they were looking for back then. And then in the 1990s, it became much more common to look for these AVO classes, so that differences that they were observing in terms of the near angle versus the far angle really became more solidified, and the theory behind them more understood. And so there were a couple of seminal papers, one by Rutherford and Williams in 1989, and then Castagna's paper in 1998. And so what those ended up showing is the different classes So in this case, this is the Rutherford um, different classes that he defined, where we had our class 1s, our class 2s, where we would see a brightening and not have too much of a reflection on the near angles, and then our class 3s. And so I'll talk about all of those in more detail later on, but it's just all part of that, realizing that there were these direct hydrocarbon indicators in seismic data. And so there's a wide range of hydrocarbon indicators. I've mentioned a lot of them from different amplitude changes on the stacked sections. You can also see amplitude shadows underneath the hydrocarbon zones. You've got different velocity changes. So we've noticed with different rock types, we often have a pull up. Well, in the case of having hydrocarbons present, you can now have a push down or kind of like a sagging. You've got different polarity reversals. You could have different phasing of the wavelets as they go through hydrocarbon. And then there's frequency changes that happen. The thought is that the gas attenuates some of the frequencies. So it kind of causes a lowering of frequency beneath the reservoir. I already talked about flat spots. So those are flat spots that occur in the seismic where we have that fluid interface. We can also get these gas chimney effects. So those are other hydrocarbon indicators. Where you kind of see a deterioration of the data quality, maybe a little bit of sagging or push down in time and distortion. And then you've got those changes in amplitude with offset, so those AVO type effects. And then there's even more, which is great. But we have the structural conformity that I talked about, because the hydrocarbon limits need, they should mimic, unless there's some sort of differential pressure going on, they should mimic the structure of the reservoir. And so we want to pay attention to those too. All right, so let's continue keeping going in this. So here's an example of a 1D kind of acoustic impedance model of gas versus water. So in the case of a bright spot, as we have our shale here above and below our gas sand or our sand reservoir. And in the case of water, we would have less of a reflection coefficient than we would in the case when we go from shale to gas. And so you could kind of look at the length of that acoustic impedance change as the reflection coefficient, so that difference. And so as you go from gas to water, there is a clear difference typically. And so that would be what's causing the bright spot. And a phase change, as you go from shale to water, you have an increase, a positive reflection coefficient. But as you go from shale to gas, you've got a negative one. And so that means the polarity of the wavelet in your reservoir is going to flip as it goes from the gas leg down to the water leg. And then a dim spot is the opposite of a bright spot, where you have a higher reflection, a higher amplitude in the water leg of the reservoir than you do in the gas leg of the reservoir. So just to go through these in more detail because they're so important, this is a case of a bright spot. So I've already mentioned a lot of this. I know when I was at Chevron, one of our rules of thumb is that we wanted to make sure to even start to call it a bright spot, at least in the Gulf of Mexico, kind of Miocene shelf area. We wanted that amplitude to be 3 times the background amplitude. And so that's something we always kind of use as a rule of thumb. And so we've got these lovely images of bright spots here from the Cox chapter of a textbook, where we can see the brightening because of that lower velocity gas in this example. Dim spot is, again, like I mentioned, where we have a higher reflection coefficient between the shale and the water leg than we do between the shale and the gas. In this case, we've got an oil-water contact, which is very difficult to see. I mean, it's just very subtle, but the reservoir is thick enough so that you could see that fluid contact between the top and the base. And you can notice, if you look along this green line, and I'm trying not to go over it with my pointer too much, that blue amplitude is very, very subtle. And then as soon as we get into the water leg, it brightens up quite a bit. So that's an example of a dim spot. And then a polarity reversals. These are some of the hardest to find if you're prospecting. So here we've got our polarity reversal, or a phase reversal as it's sometimes called. And we go from the top of the gas sand, where we have the gas present. And then when we get into the water leg or the brine sand, you can see that that polarity reversal switches. So it utterly flips color. And sometimes they can be hard to find because you can confuse them for a fault. Or some sort of other offset, maybe just in really noisy data, you can't be very confident of it. And over here is another example of a polarity reversal, again, really zoomed in, where we could see how we flip from the red down into the blue from this other textbook example. I've only prospected in one field for these, and it was very, very difficult to look for hydrocarbon indicators for polarity reversals. And then that flat spot you could see in any of these types of reservoirs. And you could also kind of just see it by itself sometimes. And so this is where you get a reflection within the reservoir itself, so typically between the top and the base of it, and it looks flat compared to the dipping strata around it. If you're working in time data, you also want to keep in mind that it may not look perfectly flat because of velocity differences. So it may be kind of cocked or at a little bit of an angle. And you can see that here, how the flat spot is dipping just a little bit. Here's some more examples where we've got an offshore Borneo from the Hart textbook. We have a really lovely bright spot. It really stands out. And then we have a flat spot associated with it too. Here's another case where we've got the bright spot, and then we also have a flat spot right down here. And so you could see as you move from the hydrocarbon leg down into the water leg. And they also point out some other potential accumulations too. Again, with that question mark that I love putting in my interpretations when you're not quite sure, but you have an inkling or you want to point it out. You can also use the optical stacking technique to kind of bring out these flat spots a little bit better. And so this would be, instead of stacking a bunch of time slices like we talked about in module 2, I think it was, instead you could stack vertically. And so you can imagine if you're peering through a semi-transparent reservoir, that flat spot and that kind of like turn off of those bright amplitudes might become more apparent if you're looking at a optical stack than just at one inline or vertical section. And so this is just a nice summary from the Brown textbook. I like how he shows in here. So we've got this chart that I've talked about a few times in different formats. But what I like about this figure is just how he shows the amplitude decrease as we go from the hydrocarbon leg into the water leg, but then also the polarity of the fluid contact in there. And so I like it as a nice summary. Okay, so I talked about conformance to structure. And so this is an example with a synthetic model from the Hart textbook, where we have the synclinal structure or anticlinal structure. We've got our gas sand on top, so it's kind of pooling on top. And then we've got water beneath it, okay? And so just a nice classic dome. When we look at what it looks like in seismic, you can see that the amplitude looks much higher. So we've got that bright spot. We also have a flat spot, okay? But notice how we're working in time here. So that flat spot actually kind of seems to dip down and sag a little bit, which of course makes sense when we consider the lower velocity and lower acoustic, the longer travel time. My dog's behind me growling a little bit. I think he wants pets. So sorry about that. Okay, so it's a little bit longer. And so the other thing that we notice here is, pet him, is when we look at that in a structural view and we put those time structure contours on there, we can actually see how that bright spot, that higher amplitude, conforms to structure. And so this is another key DHI, structural conformance. These are some examples in more real-life seismic data. Here's an example from the Brown textbook right here, where we could see kind of this conformance of these more teal bluish colors to structure. And then in this case, I think I may have need to edit these slides, but this is another case from the Sims and Bacon textbook where they show a flat spot too. So not a fit to structure, but a flat spot. Here's another case from the Hart textbook where they show a structural map here. So we've got our contours laid on it. We have some faults in the area, a couple of wells. And when we look at what the seismic amplitude looks like, we can see even though these aren't overlain with each other, we can see that the amplitude, the higher amplitude does seem to roughly conform with where we would have those structural contours. Here's one more example. In this case, we have a gas cap that seems to be brighter down to like the yellows or so. It tends to conform to structure, roughly, if we look at that structural contour. And then we have our oil leg, which is a little bit of a dimmer green, light blue. And then we end up in the water leg. And so we could see both of those fluid contacts conform to the structural contours. And then here's a nice DHI, a fit to structure. Now this time looking in more of a three-dimensional view. So this is the Genesis field. And what we've got here, it's kind of cool. So I'll spend a moment on it. We have our oil-water contact. And so you can see it dotted here and labeled as OWC, oil-water contact. And we can see the higher amplitudes above that. But one thing that's kind of interesting is you can see there's a fault in this area. And you can see a smaller fault right off to the side here that I'm trying to point out. And one of the things you'll notice is that the oil-water contact only goes to that fault. Okay, so it kind of, it seems like the hydrocarbons are only above the tip of that fault, which suggests that at one point, this fault was probably allowing further migration, or it was leaking the hydrocarbons out. And we do notice a faint signal in here of perhaps an area where there used to be hydrocarbons. And so I think they call it an ROWC potentially. So maybe a remnant oil-water contact, so like a paleo contact where the hydrocarbons were before they were able to leak out through that fault zone. Okay, so one of the things you always want to keep in mind is that even though hydrocarbons can cause amplitude anomalies, they can also be caused by different things. And so I always like to remind my students of this. So you have to keep in mind changes in lithology, so heterogeneities, overpressure, and the presence of hydrocarbons. So those are kind of some of the main things that can cause these different amplitude anomalies, besides all of the things that can change the amplitude that we talked about in like acquisition and processing in the earth as an attenuator. Okay. So I also mentioned, wanted to mention a little bit about shallow gas and gas chimneys. And so in this case, we have a gas cloud right in this area, and it actually dims and attenuates the seismic amplitudes below it. And so you could kind of see that below the gas cloud, which is above us a little bit, you've got a dimming of the amplitudes. And so that's something you want to pay attention to and just be aware of, that even though we're still talking about hydrocarbons, we're not, and we would kind of technically see a dim spot if we mapped out these horizons. It's not being caused by hydrocarbon necessarily in this reservoir, but rather from the attenuation of the amplitudes below the higher gas cloud. And then over here, we have some examples of gas pipes, or blowout pipes as they call them, where you have thermogenic gas that's migrated upwards. And so oftentimes you'll see pockmarks on the seafloor in these regions. So gas chimneys is another word we often call this. And so that's very typical of what they look like. And of course with DHIs, there's a lot of pitfalls. I think a lot of these you learn over time, and companies have learned over time. So oftentimes when you have prospect failures with DHIs, they're often attributed to those unusual lithologic variations. You could also have fizz gas or undersaturated gas or uneconomic gas, as we might call it. You can also have superpositioning of seismic reflections and different tuning events that cause those anomalous amplitudes. And then you could have seismic signal contamination by multiples or noise. And so I'm going to show you some examples of these in the next couple slides. And I also wanted to mention one case that I came across was when I was working at Prospect up in the Barents Sea. I was doing reservoir properties from Seismic, and we were given the seismic data from the business unit we were working with, and we weren't giving the processing report. So now you know why I always talk about getting the processing report. And so one of the things we didn't realize is that the seismic contractor who did the processing applied this method called spectral whitening, which kind of artificially boosts some of the higher frequencies and amplitudes to improve the structural and stratigraphic interpretation. But in doing so, they ended up tainting the amplitudes at the reservoir level, and it ended up masking the DHIs. So that was an interesting lesson learned. We lost a good, 3 or 4 weeks worth of work on our team for that. Okay, so I want to mention here that residual saturation can often appear as full saturation. So we can't tell the difference necessarily between, say, 5% gas saturation versus 100% gas saturation, because the rock properties are very similar in those cases. So sometimes we could see the difference between an gas over oil over water cap. Sometimes we could see the residual oil difference. It's a lot harder to see the residual gas difference. And so those are things we always want to be aware of if we're doing economics or risking. And so this is a really classic case of fizz gas or undersaturated gas. And so the story behind here is that a company drilled the King Kong prospect in the Gulf of Mexico. And so you could see we have very lovely bright amplitudes. It was successful. And so they noticed, not too far away, I think this was a couple of miles, you go down structure and back up structure again, and against this fault, or there was a fault there, you have another series of stacked high amplitudes. And if I wasn't pointing this out, you would probably look at these and say, yeah, they look really similar. We should drill it. And that's what they did. But they didn't find commercial pay. Rather, they found fizz gas or undersaturated gas. And so it wasn't an economic find. And I think the latest thought is that the fault that was near that probably allowed the gas to kind of migrate on upwards. Unusual lithology is also something we need to be aware of. So you can get a false flat spot. And so this is the case of a flat spot due to an opal cristabolite transition. So you can kind of see it right in here. This is a case of a flat spot in the northwest shelf of Australia. And so hopefully you can see it right in here. I'm talking about it during a pitfall section. So this was another dry hole. And they figured out that this flat spot was likely a paleo contact, again, due to diagenetic effects. All right, here's another bright spot with a flat spot below it in the Nile Delta of offshore Egypt. So nothing wrong with this one. This one is a legit example. And here's another flat spot right here. So if we were in class, I'd make you run up to the board and point out what you see. And so this is the Troll Field in Norway. And this is actually a 9-kilometer flat spot. And it's Jurassic age rocks that are 28% porosity, which I just think is pretty cool. Okay, so now I'm going to pause and I'm going to see if you could find the flat spot. And if I was doing well, I'd cue up some Jeopardy music. Or you not find the flat spot, but find the DHI. It's not a flat spot. All right, so right in here, we have a polarity reversal. If you can see it, I'm trying to circle it with my pointer. And so from the Brown textbook, there's a lot of different questions you can ask yourself when validating a DHI. And they're probably more updated now. I know we had a more comprehensive list when I worked at Chevron of all the different things we wanted to consider. A lot of them have to do with how many different hydrocarbon indicators do you have. If it's just one, you may not be quite as confident that it's actually due to hydrocarbons, but rather the more you kind of have with the conformance, the flat spot, the bright spot, all of those, a velocity sag, the more of those you have, the more confident you would be in the DHI. Another interesting feature that we can see a lot of times, and I like to talk about in this lecture, are gas hydrates and bottom simulating reflectors. And so this is an example from the Hart textbook. And we get these bottom simulating reflectors because we have gas hydrates in the shallow sediments, like kind kind of like on the continental shelves. And sometimes those can actually collect free gas below them. And so since the hydrates are stable at certain temperatures and pressures, they tend to mimic the kind of like stability regime mimics the seafloor. And so that's why they end up looking a little bit flat or are bottom simulating reflectors, depending on the topography of the seafloor. And so here's an example from offshore India, and I'm trying to trace the BSR. You could kind of see it really clearly right in here, but it actually goes up a little bit further too. And so that's an example of an interesting cross-cutting feature that we can observe in seismic data. And these can act as hydrocarbon traps. So something to keep in mind. Let's see, and part of this is interesting because the BSR, it ends up having a higher acoustic impedance than the gas layer. And so if you look at this image right in here that I'm trying to show you, we've got the relative or the acoustic impedance. And so you can see how you have a large acoustic impedance difference between where you have those gas hydrates forming in the pore space and the gas below it. And so that allows that brighter reflection to happen. Okay, so let me just wrap up with a few key amplitude anomalies concepts. So seismic DHIs, they're typically these anomalous seismic responses that we see that can be due to the presence of hydrocarbon. We call them indicators, not definitely there indicators. So DHIs, they're just indications that possibly there are hydrocarbons there. So something to keep in mind. A lot of them are due because of that acoustic impedance difference for when you have gas in the pore space rather than the brine, or oil as compared to brine. And ideally, you want to have several indicators present to help you reduce the uncertainty that it is due to hydrocarbons. And as I mentioned before, there's a lot of different DHIs. I covered some of the main ones here today. And there's, of course, many, many pitfalls in our seismic interpretation. So thanks for listening once again.